Our third and last seminar on cold fusion. For our speaker, last but not least, we have pioneer in this field, Dr. Steve Jones from Brigham Young University. Dr. Jones got a BS in physics from BYU in '73, PhD from Vanderbilt in '78. In between, he did research at Stanford SLAC, the linear accelerator, postdoc at Cornell. Then he did work at Los Alamos Mason facility. He has been at BYU from 1985 to present, and began his research on cold fusion, I believe, with muon catalyzed cold fusion. And so he had publications on this long before the controversy started 3 years ago. As I mentioned last week, he's not in agreement with what Dr. Miles had to tell us. And he has a short videotape to show. And if you can't see it, come on down closer. It's only going to last a couple minutes. I believe it's has to do with a simulation of the muon catalyzed cold fusion.
Getting this is Sorry. Focus the screen. I'll let you interpret it as you wish. Try to make any interpretation of it. I'd like to start by pointing out that the work I'm engaged in, cold nuclear fusion, involves many collaborators. It's not just myself, you understand. And I'd like to give, of course, credit to the team that's working on this. In addition to my colleagues at Brigham Young University, we have associates at Los Alamos National Lab. We do have an active collaboration with Howard Menlove, Mike Picciotti, and others there, and so on. I won't try to read through the entire list, but there's quite a group. Our work was supported by DOE. That ended last December, turns out. We're still supported by the Electric Power Research Institute in our work. By way of introduction, I'd like to ask you to think with me a little bit about the energy consumption on the Earth going back a few thousand years. Okay, what we find is that we live in a very privileged period. We're burning up fuels, primarily fossil fuels. That's what we have quite a reservoir of. But we're burning these up at a much greater rate than has ever been the case in the history of the planet, as far as we know, of course. And in fact, what we're living in, if you look back, several tens of thousands of years, however far you'd like, we're living in a delta function in terms of energy consumption. It's very steep, this rise. It started about 1840 with the Industrial Revolution. Unfortunately, we have to keep in mind that our supply of fossil fuels is limited, and this will fall off very rapidly also. We're aware of that, but at the same time, we're burning fuels at a horrendous rate. And our society depends on cheap, abundant fuel. What are we going to do in 30 years when the cheap oil is gone? It's not entirely clear. Elect a new president, I guess. It'll solve probably not that problem, but probably what we'll do. Anyway, it is a major problem that we have to consider. And therefore, when someone comes along with a suggestion that he has a solution to fusion energy, then that, of course, attracts a lot of attention, and rightly so. Fusion is the basic energy source in the sun. I was going to say something about solar neutrinos. We don't understand everything, even about our own sun, but in any case, fusion certainly provides energy in the sun, and as we burn hydrogen isotopes in a thermonuclear way, then we extract a great deal of energy from hydrogen. I've written down here an equivalence for you so you can appreciate how much energy is available in this fuel, hydrogen, or isotopes of hydrogen. Through fusion, we can extract from 1 ounce of heavy hydrogen. I'll define that momentarily. The energy equivalent of burning 70,000 gallons of gasoline. Now that would even fuel my car for its lifetime. It's a lot of energy if we could just extract it. There are several approaches to fusion. The thermal fusion. We used to just say fusion. Now we have to say hot fusion, so we know what we're talking about. I promised to point out the isotopes of hydrogen. There are 3 forms. Ordinary hydrogen has a proton in the nucleus. Deuterium has a proton plus a neutron. And tritium is characterized by 2 neutrons and a proton. These are the 3 isotopes of hydrogen. So when I say P, I mean proton, D is deuteron, T is triton. Thermal or hot fusion is generally going to have to use this reaction between deuterium and tritium because it proceeds most rapidly at temperatures that we're trying to reach and sustain. The sun is actually very good at what it does. It heats up the hydrogen isotopes, and then you get fusion at a considerable, actually it's a slow rate, but it's what we live on here on the Earth, primarily, is that fusion reaction on the sun. Well, on the Earth, we use these isotopes, we heat them to about 100 million degrees, trying to imitate the sun. Then we have to confine that hot plasma somehow. Magnetic and inertial confinement schemes are being worked on. Of course, the sun uses gravitational confinement. And the joke is that as we increase the scale, these machines seem to work better and better. When we reach the scale of the sun, we'll finally achieve controlled fusion. And it is a substantial problem and a worthy goal to try to control fusion energy. I think considerable progress is being made by those studying hot fusion. This picture comes from the Joint European Tokamak in Culham in the United Kingdom. The scale is about 30 meters tall, this particular test device. Now, a number of years ago, actually in 1948, I'm forgetting now, 47, 48, F.C. Frank in United Kingdom and Sakharov in the Soviet Union, subsequently, but about the same time, suggested a novel process for achieving fusion without the need for high temperatures. This seems surprising that we would be able to get fusion without high, tens of millions of degrees centigrade, but in fact we can with the catalyst. For example, this slide, by the way, I made in 1979, and it's entitled Cold Fusion. We've been calling muon catalyzed fusion cold fusion for at least 30 years. 40 years, I guess, roughly. Anyway, the muon can induce the reaction. I won't go through this in detail because I have a video to show you of how this works, but the idea is that the muon is added to a mixture of deuterium and tritium, and the fusion then proceeds without the need for high temperature, catalyzed by the muon, which has this trick of pushing or pulling, forcing the hydrogen nuclei close together. Okay? So instead of having high temperature to force it together, it's because of electromagnetic processes that the deuteron and triton are drawn together. And then they oscillate, as you'll see in the film. And fusion occurs by tunneling, quantum mechanical process, through the Coulomb potential barrier. Let's take a look at that film now, just for a minute. I have figure this out. You can help me on this, John. Try to did series of pictures to. Oh, let's see. Yes. See if I can get past that. I think it's been about 2 years since I've shown this video, by the way, so I don't get to talk about this as much as I like. Oh boy. This is our underground laboratory at BYU, but that's not quite what I had in mind. That's interesting. This is sorry about that. It says muon catalyzed fusion on it. Well, this is our, you're looking at our underground lab. That's something that I'm afraid I'm not getting what I expected here. No. This is our, well, I'll tell you what. It looked like, yeah, it was rewound. Well, it looked like it might have gotten taped over. I apologize for that. Oh, here we go. Good. There's several cycles depicted. Here you have a deuteron and a triton oscillating, held by a muon. They oscillate millions of times, actually, until barrier penetration occurs. See, both of these are positively charged, therefore they repel. And there you get fusion, and a neutron and an alpha particle go off. Now we'll see this cycle, the second cycle of this reaction. Muon comes along. Here we have a tritium molecule, and a T-mu atom forms, releasing about 2.7 keV, which, of course, breaks up the molecule. That's a lot of energy. This T-mu atom is small, very tiny, and it's neutral. It penetrates a molecule in this way. See that process? The whole molecule starts to ring. There's a resonance. This means that this formation of the muonic molecule can occur very rapidly. And now here again we have the oscillating deuteron and triton bound together by a muon, squeezed together. You see, we use the term, well, we use the term piezo for squeeze, and I'm sure where that comes in. There's one more cycle. We'll look at this one more time. This film was made at the Idaho National Lab, where I worked before going to BYU. So the muon forms first an atom, in this case a T-mu atom. It could be D-mu, deuteron-muon atom. The atom is really very tiny because the muon is so heavy. So this neutral atom can penetrate the molecule. It's this resonance that was predicted by Russian theorists back about 78 that led to a revolution in the field of muon catalyzed fusion, because this formation is essential to fusion, and it occurs much faster, about 1,000 times faster than was predicted. We measured the temperature dependence of this process for the first time, and we're very happy to do that. Now watch, the muon this time sticks to the alpha particle, you see? As the alpha whizzes away, the muon goes with it, captured. That's the end of the cycle, typically, and that is the sorry. Well, yes, the Coulomb forces can be calculated classically, but of course, to get the barrier penetration requires some fairly sophisticated, well, it's not that sophisticated, but quantum mechanics. It was first worked out by J.D. Jackson in 56, 57, after the discovery of this process by Alvarez. Of course, Alvarez was using a proton deuteron instead of DT. Okay, well, we wrote an article, a friend of mine and I, it's published in 87, and we called it cold nuclear fusion. I'm trying to convince you that it's not that astounding to have fusion at room temperature, but you have to have some sort of catalyst. I'm going to just go ahead and skip some of this. Let's see. I'm going to start talking about this other infamous topic, which we now call cold fusion. I have to do a test on you to make sure you say nuclear before we go on. Clint Van Sicklen and I wrote a paper which we called piezonuclear fusion. This was published in 1986, March, JPhysG. We wrote it, though, in 85. And the idea here, I worked out some of the ideas, and then Clint did the math. He's really super at the quantum mechanics, and so he deserved to be the first one here on that. But the idea was to consider the idea, the notion of getting fusion by squeezing together deuterium nuclei, deuterons, without muons. Okay, that's what we now call cold fusion, but we called it piezonuclear fusion to give this impression of squeezing the nuclei together without muons. So, and we even considered the possibility of hydrogen in a metallic solid, metallic state, and considered what would happen. And also we talked about fusion, piezonuclear fusion in Jupiter. By the way, there's a term here I want to call your attention to. Let's see if I have a pencil. I have one somewhere, but does this work? Excess heat. I think that's kind of interesting. That's just coincidental, right? Anyway, we did talk about these ideas back in 85, and we pursued them. In 86, I went to BYU just after submitting that paper, actually. It was submitted in June. Went to BYU in August of 85. In 86, oh, I need to back up one step. Well, I've got this up here. This is from my logbook and shows the idea of what we were then calling electron catalyzed fusion instead of muon catalyzed fusion. We had this idea that the electron was fundamental in this process, if it would occur. Of course, this is all theoretical. We talked about using platinum and palladium, lithium, aluminum, so on. And this is, again, back in 86. This one we had notarized because my friend Professor Jan Rafelsky was visiting BYU on this day. We met as our group, our research group, and these are just my notes. And Rafelsky said, well, you ought to have this notarized. I don't do that usually. I don't think most of us do. But I'm glad I did because several years later, 89, there came along this other team working on similar work, and that happens in science very commonly, actually. They happened, though, to be quite close by. They're at the University of Utah, and I was asked to to review their proposal, which I did, and somehow they got the idea that if we were working on this, we must have taken their idea. That's not the case, and I actually showed this to Pons and Fleischmann and Chase Peterson, and it was the president of the University of Utah, and we had this notarized page. I thought that would lay the question to rest, but it didn't. Anyway, we have been working on this for many years, and we didn't steal their idea. And the use of palladium we had worked out long before. Well, let me just give you a little more of the history because it relates to what we're doing now and to why we're interested in this. You see, I gave a colloquium on March 12th talking about electron catalyzed fusion or piezonuclear fusion, and Professor Paul Palmer, this is his logbook. You saw mine. This is his. Obviously, his is more. Students take note. You want to have a detailed logbook, okay, some sort. This is more than we usually do, but this is nice. But anyway, Paul had this idea that maybe fusion could happen in the Earth. He made that jump in imagination, and he had this notion that perhaps the rock somehow catalyzes the reaction. See, somehow getting the hydrogen isotopes into the rock, into the mineral, is important in the process. Okay, now this is 86, right? I can tell you, Paul Palmer is a man of highest integrity. He didn't write this up in 89 or something. Okay, he really did. This was written in 80s. Of course, we have tons of witnesses. There's no question. But in most minds. Anyway, we had this, and the idea is that as water, including some deuterium, about 1 part in 6,000 in ocean water, is carried deep into the earth by plate tectonic action. You can possibly get deep in the earth where there's high pressure, you see, and some temperature and so on. You can get fusion reactions. That was Paul's jump. We talked about piezonuclear fusion. He said, well, maybe it happens in the earth, and that would explain why you get so much helium-3 coming out of all the hot spots. He knew of that correlation. I didn't know that, but Paul made the connection between piezonuclear fusion and helium-3 coming out of volcanoes in the earth. Of course, another test of this, you see if there's fusion, you should also get occasionally some tritium produced. DD fusion would make tritium, which would decay to helium-3, but that half-life there is about 12.4 years. So that if you saw tritium, you'd know that it had to be produced within recent times. Geological times are thousands of years, but here if you could see tritium, well, there is some evidence for tritium at the end of my talk if I have time, or someone asks, I'll show some of that evidence, but we suggested that there should be, in fact, we found some evidence for tritium coming out of Kilauea, and recently geologists have looked at Kilauea, Mount St. Helens, and now about this time, I think about 1st of March, they're going. A couple of geologists are going to the Pacaya volcano in Guatemala, Pacaya, something like that. So it did stimulate quite a bit of research, and tritium, beyond what can be explained by any mechanism that we've thought of, was found in Kilauea and Mount St. Helens by Fraser Goff of Los Alamos and Gary McMurtry, Hawaiian Geophysical Institute, and their colleagues. Anyway, so that stimulated a lot of work. Well, back in May of '86, then we started our experiments using what we called electrolytic infusion of hydrogen into metals. It just happens that this is an easy way. You see, like Paul says, get common metals and hydride them by chemical means at our instant disposal, and to test them, get D2O and so on. Well, an easy means is electrolytic infusion. In June, we started gas loading deuterium into metals. This picture, by the way, you see that picture? It does look a lot like this picture here. It's just, it's amazing, but it's true. It just happened that we were both looking at something similar. But if you think about it, how are you going to get deuterium into metals? Well, there are easy ways. By the way, I made it to the front cover of Time. This is me here. See that? I'm covering I don't know why, I just covering my face, but that's me right there on the front cover with the hand in front of the face. Oh dear. Yes, what a story. Well, I'm going to try to move along. Some of you have seen our paper. This paper was more widely read than our 1986 paper on the same subject because we had some unexpected publicity. But what we did, and there's a jump here. I should say that in '86, when we started these experiments with electrolytic cells, we had a simple neutron detector. And we did look for neutrons. We had an indication of some possible signal. So there's a group at BYU that has been developing neutron detectors for years. And this is what they came up with. But anyway, we decided that we had to have a state-of-the-art neutron detector if we're going to make any progress in this field. And the guys working on this detector, Bart Zier and Gary Jensen and J.C. Wang, so on, later joined them. Anyway, tried to get funding for it, and were not able to get funding for the detector development. It took them until '88 before we had this spectrometer working. And with this device, we're able to actually determine the energy of neutrons to some accuracy. It's not very, very accurate, but there's some energy information that comes. And this is our original data that we took with the heavy water cells And this was published in J-Fusion Energy. Actually, this plot was also published in Nature in January of 90, if I remember correctly, as a letter correspondence. Because we felt we needed to reanalyze the data set to determine if the statistics were good. Some had questioned our statistics, particularly vocal person at CERN had suggested we only had 2 standard deviations, but he, it turns out, was dealing with a subset of the data. I think he misanalyzed it, but in any case, it was just a subset of the data. Well, when you take the entire data set and analyze it, what we did is we did a fit to the background. Dang, I have the background. I'm sorry, but it's just smooth, and this is the fit we have is to the background is in blue. And then for the foreground, we add a term, a Gaussian, to pick out any bump, and it does pick out this bump here. Then you subtract the background from the, in other words, you subtract the blue fit from the blue and green, scaled, of course, scale the background, and then you get this distribution. It turns out that the center and the width both correspond to what we expect for approximately 2.5 MeV neutrons. So, that's hard to express in terms of statistical significance, the fact that the energy is correct for fusion. But that's the way it turned out. And by the way, the significance here, 6.1 plus or minus 1.5, is about 4 standard deviations, which is not bad. Certainly better than 2. And the mean rate was 0.14 per second, as we published it in our paper. Data are given there. I want to show you that, and I have permission to this, that others have also seen neutrons from this similar process, or same, electrolytic cells, and also at 2.5 MeV. These data, I asked Kevin Wolf at Texas A&M if I could show it. He said I could. Presented this back in April of '89. Here he has a cell that's kicking along, and then after about 3 hours, the rate suddenly increases over the normal background level, as you can see. And what he did, and this was a good thing, he was there, he moved the cell 5 inches from the detector, the rate dropped, as you would expect from 1 over r squared dependence. Isotropic emission of neutrons. You move the sample back and the rate drops. Then you put it close again to the detector and the rate was back up. Now then without changing the cell parameters, the signal turned off. That's characteristic of what we're observing. Some onset of signal and then some drop off. And this can last for minutes, it can last for hours or days. But the other thing about it is that the energy of the neutrons, he measured. Now, what I have to say is that he used Ne213, which does not give you a nice heat the way the BYU spectrometer does, but it still gives you energy information. It gives you this sort of a bread loaf shape here with a shoulder on it. And if you compare then with data, there's one set of data. The Monte Carlo calculation is in red. That's what you expect, in other words, for neutrons of 2.5 MeV energy. And the orange dots are what are observed, and the same with the purple, observed from a different run. And in both cases, you can see that the agreement with the Monte Carlo calculation is pretty good. What this means is that the neutrons that were observed at Texas A&M are consistent with 2.5 MeV neutrons, just as we found at BYU. Others have done that too since, but I won't show you all those data. Okay, in particular, the Japanese have done some. If you'd like to see these other data, I'm going to leave this book with John Dash. This is proceedings of the meeting held at BYU on called Anomalous Nuclear Effects in Deuterium Solid Systems. We decided not to use the term cold fusion. It had picked up a bad name somehow. And you'll find in here, though, the work of ours and Wolf's and Menlov's and the Japanese. I refer to Takahashi, shows 2.5 MeV neutrons, and charged particles and all sorts of good stuff, geology. And question? That's hard to explain conventionally, right? If it's uranium or some contamination, it shouldn't do that, right? It should be pretty steady. Well, it depends on the contamination, but uranium half-life is billions of years. I wouldn't do that, for example. Why does it stop? That begs the question, what's going on here? In fact, I think I'll go ahead then and turn to a little theory before I show you more data. What is it? Could be anything. That's weird. That's exactly what I came up with, too. We don't have a good model for this. The paper that Clint Van Sicklen and I wrote back in '85, I have some ideas, but we missed the fusion rate by orders of magnitude. We can't explain it that way. One model that has been suggested at Los Alamos and Washington State, these guys, is called fracto-fusion, in which you get a crack in deuterium and tritium. This would explain bursts of neutrons, probably, but it's hard to explain a emission of what we call random emission, uncorrelated neutrons, over a period of hours. This would explain a burst in microseconds, perhaps, or nanoseconds. What's going on here is that as a crack forms, the idea is that you can generate separation of charge, which accelerates deuterons and results in fusion in that way. The model has some problems, but it is one to explain some of this. Of course, what you could say is that there, for some reason, is phase change or buildup of deuterium that leads to cracking over a period of hours. And with each crack, you have a certain probability of generating fusion neutrons. Look, if you're asking me for a numerical solution, I don't have one, but we do have some ideas that we're looking at. This is a comparison of hot fusion and muon catalyzed fusion. Hot fusion on the left, where we have high temperatures. They're still tunneling through the Coulomb barrier 100 million degrees. The sun isn't even that hot. The core of the sun is only about 10 million degrees centigrade. So they're still tunneling through the barrier. What happens with muon catalyzed fusion is that the barrier width is decreased dramatically. There's some screening of the Coulomb potential. And so the tunneling through the barrier now takes place very rapidly. Actually, when you form a DT mu molecule, the tunneling occurs in about a picosecond, 10 to the minus 12 seconds, which is less time than it takes to explain what's going on there. Could be that in cold fusion, there are regions where the concentration of deuterons is particularly high. This is one that I like it because it's in our original paper. The general notion is, and that is that perhaps we form in small regions in the lattice or the solid, whatever the solid is. We form regions of extremely high pressure. Now, John Dash's work shows, for example, there are pores in palladium after you've loaded it with deuterium. That means little spots where the deuterium has evidently collected and done some damage to the metal, right? That means it's under high pressure. And the suggestion is that if you look at the possibility of forming metallic deuterium under very high pressure conditions or something approaching metallic deuterium, that what we did is we looked at some Monte Carlo calculations. These are quantum Monte Carlo calculations by Chepperly and Alder and published here. You find that the separation between deuterons is, well, let's see, I guess I don't have it listed here. In a molecule, it's 0.74 angstroms. I can't get that to work right. But anyway, that's 0.74 angstroms in a molecule. In the lattice, the separation is no better than that. It's about, the lattice constant typically is larger than that. So you're not going to improve that just by putting deuterons in a lattice. If you get deuterons in a single interstitial site, you can improve somewhat on that, but that's a very high energy condition and not easy to maintain. However, if you can get deuterons to form a metal state, okay, we usually think of hydrogen as a gas. Well, we can liquefy it. If we squeeze it enough, it'll become a metal. And that's very difficult to do, actually, but the notion is that if we form metal, that perhaps under those conditions, we have piezonuclear fusion because the deuterons are bound, right, in a lattice of their own, a metal lattice, and that the tunneling can occur more rapidly. Even there, it requires some transient condition, some shock wave or something, but that's as far as we've gone on that idea. And I think it's one that can be tested, and we hope to test it soon by using a diamond anvil cell to reach extremely high pressures. Okay, there's some, is it wrong for me to talk about experimental data for which I don't have a definitive hypothesis? I mentioned one that we'll test experimentally. We hope to. It's not easy getting metallic deuterium. We'll test it. But, is it finished? No. But what's the dark matter in the universe? Where is it? What is it? We don't know. Does that mean we can't talk about it? I don't think so. Okay. There are many surprises in physics, and I think the name of the game is to figure out what's going on. Maybe you made a mistake, but maybe there's something interesting there. We keep making the same mistake if it is a mistake. We've seen it now at Los Alamos, BYU, Texas A&M, and as I'll show you, the Kamiokande has some interesting experimental results relating to cold fusion. Now, as soon as this became widely known that we're working on this in March of '89, I arranged to work with colleagues at Los Alamos. Actually, I discussed this work that we were doing the previous year with a number of them. That is in 1988. But in '89, they became motivated to look at this with us and set up some experiments. One of these is to load titanium chips. Well, one of them was to use electrolytic cells, as I have a picture of here. This is from the experiment at Los Alamos. We also used hydrogen or deuterium gas loading, which was done also in Italy, but we had started doing that in '86, as I mentioned, at BYU. And so you put the metal in a stainless steel vessel, you add deuterium gas, and the gas can slowly permeate into the metal. We used a temperature cycling that was pioneered by Scaramucci and his group in Italy. And then we put this in a detector with a nearby control detector. And we did see a surprise. Well, first of all, before I go on to the surprise, we did see what we call single neutrons, that is, neutrons that are not correlated in time within 100 microseconds. They just come out randomly in that sense. But we did see, and again about the same rate as we had seen at BYU, neutrons being emitted. This strange jumping around of the rate is again puzzling, but should give us some clue as to what's going on. The statistical significance of this is about 10 standard deviations. And the nearby detector showed nothing. This sample, if this is TI1, I'm not sure. But anyway, one sample, pretty sure it was this one, was moved from the control counter, from the original counter to the control. And the signal followed the sample. And then the signal stopped. We also saw at Los Alamos, for the first time, microbursts, which means tens of neutrons in a time scale of about 100 microseconds. And that has, time's flying. I want to get onto the Kamiokande. We then, with a lot of skepticism, of course, still reigning on this, even though we're not talking about generating heat, you realize that the number of neutrons that we're seeing here is insufficient by about a factor of 10 trillion to account for heat. Now that factor is about the same as the factor between the national debt and the dollar bill. It's a very large number. And we're not talking about enough to make heat here, but we still think it can be interesting scientifically and perhaps help us understand what's going on inside the Earth and so on. So the Kamiokande group invited us to come over. They're used to looking for rare things such as neutron decay or proton decay, which has not been observed yet, by the way, and neutrino detection, which has been observed but happens very infrequently. So it's nice to work with patient people. Most, I think, scientists would like to see something happen on a time scale of hours or days, but these guys are willing to wait months. And that's what it takes in this game, is patience. Here's the collaboration. The Kamiokande is a tank of water, 2,000 tons, I guess, of pure water. And it's deep in a mountain under 1,000 meters of rock. Here's some more information. I don't think I'll go into all of that, but the principle for detecting neutrons, which is of important to us, is that any neutrons first thermalized, captured in chlorine. There's a saltwater tank surrounding our test sample, and the sample itself is kept in a stainless steel vessel. Anyway, the neutrons get captured in chlorine, which then the chlorine gives off a high-energy gamma ray, and the gamma produces, mostly by Compton scattering, a high-energy electron, which produces Cherenkov light. Light. I won't go into the details of Cherenkov light, but Cherenkov light is what is detected in the counter. And it works out that there's not much that can give this Cherenkov light other than some charged particles zipping along in this water. Cosmic rays are very easy to rule out, by the way. Besides all the shielding that you've got to knock out cosmic rays, you've got a veto counter. And then the entire counter itself is sensitive to these charged particles whizzing through. So there's no more question about cosmic rays. Here's just another picture of this setup, or diagram. And here's an actual picture. If you look at this apparatus, this is what it looks like physically. There are two pictures of it here. As we're loading one of these cylinders now into the stainless steel vessel, which is also inside an acrylic vessel filled with salt water. Then this entire thing is loaded into the Kamiokande. By the way, the water in the Kamiokande is viewed by about 1,000 photomultiplier tubes. So we can keep track of the light that's generated by Cherenkov or by cosmic rays. Well, that'd be Cherenkov also. Let's see. We have 15 minutes left, right? A little time for questions. Let me see what I can do here, talking about how we identify neutrons clearly. Let me just point out, we can see this Cherenkov light, and then we can reconstruct the vertex. The Kamiokande group does that, of course. They're used to doing that, and they reconstruct the vertex. We want to know if the source of light came from the center of this tank of water, which is where our sample is, or did it come from some other place? We keep track of both, by the way, both the center of the chamber and outside of it, because, and there's calibration with californium neutrons, but you see, the sample is in the center, and then outside of that we have a region where neutrons, or the gammas, very rarely get so far out. So that gives us a measurement of the background concurrently with our sample. See, the detector is so huge, it's effectively a segmented counter. The inner part where we have our sample, and the outer part where we don't have a sample, and we can just see if the background's changing, for whatever reason. Doesn't matter why. We have a concurrent background, very nice feature, and that is subtracted from any signal we see. The samples that I've got some more detail here, but I don't have time to go through all of that. We looked at pressurized, that is deuterium gas, on mostly titanium cylinders starting in January last year. We looked again in July a little bit. We looked at electrolysis cells for quite a long time. And then we started in April one set and July a second set. And then we've also looked at heavy water cement. Actually, we've looked at a few other things too, but these are the areas we've concentrated on. Heavy water cement, that idea came from Paul Palmer again. The idea is that if you're getting fusion in the Earth, what sort of processes occur in the Earth? Well, hydration reactions are common, and that's what makes cement harden. You know that, don't you? It's not the water evaporating out of the cement, no. It's hydration. It's a chemical reaction in the cement that makes it hard. Water is required for cement to harden, and so we looked at that. And I'll share those data. It's quite interesting. So here's a picture of the electrolytic cells. About 15 to 20 cells here stacked together to load into our chamber. We did see bursts of neutrons. Here's an example from the Kamiokande of 4 neutrons. They definitely look like neutrons. And here's the vertices for these 4 events located in the center, all 4 of them in the center. And the time between, that is from the first to the second, was 12 microseconds, then 6, then 39. See. Now, we saw a number of bursts. We also looked to see where the bursts were located in this chamber, and they are concentrated in the center of the detector. We looked at the energy distribution of the bursts, compared that with the Californium calibration, and it does look very much like neutrons. It could have been, who knows what, cosmic rays or something, but no, it looks like neutrons. Now, here are the bursts as a function of time for the electrolytic cells. This is in April. Also, the size of the burst is shown. That is the number of detected neutrons, whether it's 4, 3, 2. The background that we ran was the same sort of cells, but run with light water. There's one count of 2 there. Then we used this July set. We baked out the cathodes at about 400 degrees. I have to check exactly the temperature. That was last July when I was there in Japan. And then we instead ran with heavy water, and we just got 2 signals, but one of those was 4. See, the larger the signal, the less likely it can be something easy to explain. I'll show you how we compare with uranium in a minute, which is the most likely contaminant that could explain things. Now, the April set, the way we worked that is we took these materials. You see, if there's uranium in there, you want to use the exact same materials, but somehow you got to get rid of the deuterium, otherwise you could be confused with some anomalous reaction with deuterium. So what we did is to take the cathodes and put them, bake them out in vacuum at about 600 centigrade and backload with hydrogen. We repeated that cycle and then cool. Repeated that cycle a number of times, hoping to flush out the deuterium, or at least, well, the deuterium is diffusing out, the hydrogen is diffusing in. At least we dilute the deuterium. So this is the same, exactly the same materials here. Of course, these are the same too. Here we started with H and then went to D. Here we started with D and then did what we could. Well, I should have got a better pen. And went to H. But you can see there is a distinct difference, certainly in the April set, foreground and background. Now, summarizing this, 1,000 hours of data with heavy water and, 2,600 hours, that's what we had here, in the control. And you can see that there is a difference. That is, there are more events and also larger multiplicity events in the heavy water electrolysis cells. Uranium can fit quite well, actually, the controls. Makes a pattern like that. Remember, we measured uranium. Uranium, when it decays, gives off usually 2 neutrons. 2.19 actually is the average. As you know, that's not just 1, it's usually 2, or a little more than 2. So you can get 3, of course, neutrons and so on. But anyway, the probability, it works out that the heavy water electrolysis cell bursts are due to uranium contamination from these data, and this is a lot of data now, it's over 3,000 hours worth, is less than 10 to the minus 3. So,
What's the electrolyte?
Here's the final data from Japan. The electrolyte was mixed. LiOD in some cases, and our normal acidic solution in other cases. So we had both types of cells. We remember we have 15 to 20 cells, so we can use different electrolytes. I do have a thesis by a Japanese student, it just came out, which gives in detail the composition of each cell. There's no point going through that here, I think. As comparing that with the results from the burst results from Los Alamos, we find that the rate after background subtraction, here's the multiplicity now, source neutrons, 0 to 10 we couldn't or didn't measure at Los Alamos because there's too much background. 10 to 20 we get this rate about 0.003 bursts per hour, and at Kamiokande 0.002, so it's within reason, I think. The rates are close. Now, we did not see, however, any large bursts at Kamiokande, and I think that makes the Menlove results on the very large burst somewhat suspect. In addition, Howard at Los Alamos found a problem with one of his detectors. I should tell you that a high voltage breakdown that can mimic the very large bursts. And so I really have to say that I would question the large bursts at Los Alamos, but the small ones and even the rate seem to be there at the Kamiokande and cannot be explained easily conventionally. Unless we're just unlucky. Yeah. Now we also looked at the gas-loaded chips. Picture of some of the gas-loaded cylinders, and Ishida working on one of these. We did see bursts in the gas-loaded cylinders, particularly in one sample. We must have run 15. I'd have to check the data, and it is in the thesis, fortunately, but I just don't have the number at my fingertips. But anyway, in K4, we saw 3 bursts. 1, 2, 3, 4 bursts. And here's the vertices given. The time between neutrons is right here, microseconds. The burst could be due to uranium-238, but only if the uranium is about 4.5 parts per million. Remember, we looked at uranium, we put it in there and looked at it and see how many bursts we get and so on. Distribution and multiplicities, and we know how much it takes to make this many bursts in the time, which is about 600 hours, looking at K4. Although most of these came in 3 of them came with just these few runs. Anyway, 4.5 parts per million. It was measured at Los Alamos as less than 1 part per million. We didn't see any at Los Alamos. This is a neutron activation technique, and we're hoping to get a more sensitive measurement of the uranium. But it looks like uranium will not explain these bursts either. It's not easy. Now, the heavy water cement. We started this in April, a heavy water cement. I mixed it up and put it in there, and Japanese are very patient, as I said. Let me do these crazy things. And so I put this in there, and sure enough, we saw a signal. And then 7 months later, they looked at this sample again. We were looking at electrolysis mostly in between. And lo and behold, the signal had disappeared, changed by a factor of, what was that? It was about 3 or so standard deviations. But there was no neutron signal evident at all in November, but in April, there was a clear signal. Let me show you what the signal looks like. In a way, this is looking now at the distance cubed from the center. You expect any signal to appear in the first 2 meters, which is in these first few bins here. And sure enough, there is a signal. And as you make stiffer cuts to reduce background, that signal remains. Whereas out further away from the center, the counts go away, you see. So this is a robust signal. There's no question about the statistical significance of it, which actually works out to be around 10 to minus 8 or something. Al Anderson worked that out, by the way. He was given a chance to look at these data, and he got about 10 to minus 8. But it's been seen since then with new cement signal. Light water cement shows nothing stirred heavy water, stirred in the mine to get radon. We were worried about radon in the mine getting in there. Shows nothing. But, we keep running, we keep seeing this signal. The signal lasts over a period here of about 2 weeks. Is that about 15 days right there, a little more than 2 weeks. Signal remains constant. It doesn't have characteristic of radon, yet after 7 months, the signal goes away. We don't know of any explanation or any contaminant that can do that. The distribution of hits in the photomultiplier tubes, the number of tubes that are hit, corresponds with what we expect from calibration with Californium neutrons. You see the same shape. Therefore, these are neutrons. They're not gammas or cosmic rays or what have you. What could it be? Statistics are very good. Signal to noise is high. Cosmic rays are ruled out. We've seen this now a number of times. It seems to be quite reproducible. Nothing with the light water cement. Radioactive contamination. Now, this is what we've worked on mostly. And what we've done there is to look at the dominant radioactive products. And there are contaminants, of course, in cement. You expect that. There's uranium and thorium and the daughters. And the bad actors for us are thallium. That's the one that we really worry about. 208, because that has a 2.6 MeV gamma. And anyway, we look at these other uranium-radium series as well as the thorium series, the thallium. Using a jelly detector, we can pick out these signals and determine how much contaminant there is. And then we took our detector at BYU, this one, the helium-3 type counter, and we added thorium chloride to heavy water cement and light water cement and compared. I mean, we can see what happens when there's thorium in there. We get a certain amount of neutron production because of thorium, but it turns out that it's not enough to explain what we see in all but this case here. In this case, there's enough radioactivity. It's cement plus sand. It turns out the sand had quite a bit of radioactivity in it. It's unfortunate, but we tried that. But there we can, within an error bar, 1 sigma, we can explain the signal. These others, however, are out. This one, for instance, is out by 4 standard deviations, and these others are around 3. And besides, the time dependence is very difficult to explain. And we don't think our measurements of the thorium and uranium-radium series can be that far off. We think we have it pretty well nailed. In any case, if they're off systematically, we should see, we shouldn't get agreement here. Also, the time dependence, as I mentioned, is very difficult to explain. Why should this signal be high at first and then 7 months later go away? Why should the signal increase? I realize that's only a 2.5 sigma increase, but we're either very unlucky or something's going on here that cannot be explained by conventional means. Well, to finish up, I want to show you this. We're happy about having this new laboratory 7 miles from campus where we will be continuing this sort of experiment. We feel that more data need to be taken on the heavy water cement in particular. That's something that we came on. Now, time is up, and I haven't had a chance to talk about this, but if you want to ask questions, let me show you one thing. It just take a minute, but why is it that so many scientists are angry about this research? I think it's fair to say that there are quite a few. Why is that? Why? Can anybody tell me? I don't know. Actually, I do have some clues. I think part of the problem is that the peer review, now, I think I can say this because we really tried and have continued to try to put our publications through the peer review channels. We haven't used lawyers to threaten anybody or, that sort of thing. But proposals, but the group at our neighboring institution, they that group has now left that institution. I have many friends at the University of Utah. Anyway, those gentlemen, instead of going through the normal peer review process, had a press conference. And that is irksome because what it means is that you're not trusting the system to ferret out whether what you've got is good science or not, you see. And that also they went to the state legislature, got $5 million, but without peer review. There's a lot of public pressure, media pressure, but without peer review. And they went to the federal legislature and also asked for $25 million, which would have come out of hot fusion, I was told. I also testified before Congress, and they have to go through peer review, and besides that, I didn't see any reason to think that the heat they were getting was due to fusion. I continue to think that, and the numbers we're seeing are way too small to support that, and I have other reasons too, but I can't go into all of those. Anyway, they skipped the peer review system in those cases. That angered people. There's more than that. There were some claims made, and this one also I feel fair to mention. I feel it's fair to mention because this claim that they had a hot water device that was working based on cold fusion was made in July of '89, just days before the $5 million was finally granted. And I didn't believe this, and I just still find it incredible. At the meeting held at the University of Utah in 1990, March, I showed this slide, or one like it, I don't know if it's the same one, but the same picture from the newspaper, color picture, you see, and so on. I asked Dr. Pons publicly if he would please tell us what is the status of this working hot water heater. He declined to tell me. He was a little huffy and felt that my question, he later told the press that my question was not scientific. But it seems to me that if you're making claims like this, you ought to be able to tell what the current status is. As far as I know, they're not claiming anymore they have a hot water heater, but he wouldn't answer the question. This all damages the effort, where we're trying to do some work and having people make claims like this. I have one final thing to show you, which is kind of sad. This is the original data shown by Fleischmann. This was researched out by Frank Close, and this is from his book, Too Hot to Handle. Original data shown by Fleischmann at Harwell Lab, and it shows gammas. You see, if you capture neutrons in light water, you get a gamma. It's supposed to be at 2.2 MeV. The neutron is at 2.5 MeV. What you find, and this is in the press conference, we have it on tape. You have them saying there's a bump at 2.5 MeV. That means that these are what we expect, fusion neutrons. Well, they were wrong. This is what he showed, though, the bump at 2.5 MeV, to 2500 keV. They went to Harwell, and the scientists at Harwell said that they told Fleischmann, look, your bump's at the wrong place. If it's neutrons, it's got to be at 2.2 MeV. Neutrons capturing in water gives a 2.2 MeV, not a 2.5 MeV. 3 days later, at CERN, this is what Dr. Fleischmann showed. Now, those data points look the same to me. But notice the energy, 2.2. This is kind of sad. Now, of course, Close thinks it's fraudulent in 3 days to move that. They are the same data points. Maybe it could just be a calibration error, but you see the problem with calibration error, this is what they finally showed when the spectrum came out. You see, they published just a portion of the spectrum. They didn't show the whole thing. When you look at the whole thing, you see the thallium-208 line at 2.6. Well, that nails this puppy. You can't move him down 300 K. Got this other line right next to it, and some other lines that are well known, you see. I mean, you can't just, okay. That was a sad situation, and continues to cause us difficulties as we're confused with these guys. I read recently in a magazine that I believe there are vast amounts of energy coming from a simple cell. I never believed any such thing, I assure you. nor have I said. Well, here's what I do think, though. I think these two studies are quite independent of each other and should not any longer be confused. Like this is Hugo Rossi, who had been the director of National Cold Fusion Institute. This was back in November. There's as yet, and I still think this is true, but anyway, I agree with what he says even today. There is as yet no published data from an experiment demonstrating convincingly that the energy balance is positive over its entire course, in which it ties the excess energy undeniably to a nuclear process. And with that, I'll close.